Okay, so this, as we said, we're only going to cover this chapter, and we just covered this first section. We're only going to cover actually the next two sections. So 1.2 is called More About Vectors, and then the dot product, and that's it. Let's go on. So here we're focusing on R2, in other words, like two dimensions, or the XY plane, as we usually call it. And we're just going to focus on two special vectors. So this is clearly a vector, and this is clearly a vector, and these are two special vectors. This is 1, 0, and this is 0, 1. And if you think about what that means, or where they're located, so this means 1 in the x direction and 0 in the y direction. In other words, 1 in the x direction and 0 in the y direction is here. That's called I. It's a unit vector. It means it only has length 1. And then we have also j, which is 0 in the x direction and 1 in the y direction, and that looks like this. 0 in the x direction and 1 in the y direction. It looks like this. So we're just focusing on two special vectors, I and j. You can see why we would focus on them. They're kind of important. One goes only along the x-axis, the other goes only along the y-axis. They only go in one unit in each direction, so they're kind of special. So again, 1, 0, and 0, 1. So one reason that they're special is that suppose we just take any arbitrary vector, like this one, a1, a2, then because of the way vector addition works, you know that if I write a vector, like do this, and I do this, in other words, I put the a and then 0, and then I put the 0, and I'm sorry, the a1 and 0, and then 0 and a2 like this, you know that, of course, when we add these two together, I get a1 plus 0 gives me the a1, and 0 plus a2 gives me the a2. So I can split this up like this. And then you also know about scalar multiplication, means I can pull out the a1 from here, and I can pull out the a2 from here. What I mean by that is I can say, to get this piece here, I can say it's pull out the a1, and then times 1, comma 0, because obviously that gives me a1 here, and 0 here, which is what I wanted here. And then I can do a similar thing over here. I can factor out the a2, and I get a2 times 0, 1, right? I can do that. And now notice that I ended up with these two special vectors in here, because this is 1, 0, the 1, 0, the I, and this is 0, 1, 0, 1, the I, the j. And so I can just write them as I and j, and I get a1i plus a2j. So I've shown that this vector can be written in terms of I and j like this in a very simple way, right? All I have to do is just take this thing times this scalar times I plus this scalar times j. Now be careful and notice that this plus here is not like just regular addition. This is vector addition, right? Because this is a vector. a1 times I, if I is a vector, and it is a vector, it's a two-dimensional vector, then a1 times I is still a vector. It's a scalar times a vector. Remember, it's just I and then scaled or stretched out by this factor a1. We saw that up here. We saw this if we had a and we multiplied it by a scalar of 2, it would be in the same direction as a, and it would be, but it would be of length, it would be double the length. So similarly, this is going to be in the direction of I, but multiplied, its length will be changed by a factor of a1, and this will be a vector basically in the direction of j, but it will be scaled by a2. So anyway, the point here is that I'm saying is that this is a vector, and this is another vector, so we're adding two vectors. So this plus is not just regular scalar addition. This is addition between two vectors, which may seem obvious, but it's good to point it out. And they also say, of course, you can go in the other direction. So if you have something like something written in terms of I and j, you can sort of just pull out the scalars and say, oh, that's A1, A2. And pictorially or graphically or geometrically, we can say that if A, remember what did we say? A was A1, A2, then it's, we can write it as this, we're saying here that we can write it as the sum of this plus this, and we know how to do sums. We said sums of vectors, we use that, we put, for example, this at the tip of this one, and then, so we do this, we take the first one, and then we take this one and put it at the tip of that one, and we go up to here. And this is where we end up, or this is the parallelogram rule also. That's just another way of visualizing it. And here, we do something similar, but now we have 3 dimensions, so we need to talk about 3 special vectors, not just the I and the j, but since we have another direct dimension, we'll call that k. It's in the z direction. We usually call the vertical direction the z direction. We usually put like x down here and y down there and z up here. Of course, you don't have to do it that way. You could put x here and y here and z here, but the standard way to do it is x here, y here, and z up there. Anyway, we have the special vectors, the vector in the direction of x, just like we had one here. We'll call that I, the direction in the direction of y. We'll call that j, and in the direction of z, and we'll call that k. And so if we have something A, which is has coordinates, you go A1, A2, and A3, then we can write it in terms of I, j, and k. We would say it's A1i plus A2j plus A3k. So these vectors I and j, or I, j, and k, they're called, we said that they're kind of special, and they said, so they have a special name. They're called the standard basis vectors. So standard basis vectors I, j, and k, or I, j. And we said that any vector, for example, any vector in R2 can be decomposed pictorially into appropriate vector components. So we saw that here. This one can be decomposed into this plus this. We say like this, these are the components of this A vector. We say it has this much component in the I direction and this much component in the j direction. Or actually, usually we say that it has this is the component, the I component, and this is the j component. So when we're talking about R3, we have to, when we indicate a vector, even if it's I, we have to give all 3 of its dimensions. We have to specify it as a triple. So what is I in R3? So it's 1 unit in the x direction, but no units in the j direction, and no units in the k direction. So it's 1, 0, 0. And j is 1 unit in the y direction, but none in the x direction. So it's 0 in the x direction, 1 in the y direction, and 0 in the k direction, or in the z direction. And k is 0, 0, 1. So if we're talking about I, j, and k, we would write them like this. So again, if we have an A in 3 dimensions, we can write it. We can write A as A1i plus A2j plus A3k. So she says we shall use both coordinate and standard basis notation throughout this text. So what is she talking about? Sometimes we'll write it like this, and sometimes we'll write it like this. So these mean the same thing. That's what we said. We said this can be written like this. So they mean the same thing, but they're not written exactly the same way. So sometimes we'll write a vector like this. sometimes we prefer to write it in terms of I, J, and K, the special standard basis vectors. So we can write it like this. So we should be equally at home with either writing it this way or as writing it this way. In other words, 1 comma negative 2 could be written as I minus 2j. And this one could be written this way, or this one could be written this way. We just have to get used to that. Okay, so we're all familiar with equations like this. So this is the equation of a line, and this is also the equation of a line. And if we write something like y equals 5, what we mean is, as opposed to y equals mx plus b, where here we can see that y depends on x. Here we're saying y does not depend on x. Y is just 5 all the time. So we just get a straight horizontal line with height equal to 5. Okay, so that's a standard way to write equations like this, and also like this. This is, of course, the equation for a line. So typically when we write equations, we put x and y together, and then and some kind of equation, equal sign, and so that's called the equation for a curve. Okay, but we want to try and do this in a different way. So here we have kind of a different scenario. We have x as a function of t and y as a function of t. Now, even though x and y are both functions of t, we're going to try and make a picture of this without showing t at all here. We're only going to show x and y. So we can check this for different values of t. So we can ask when t is equal to, actually I forgot to put in 0, but when t is equal to 0, what do we get? We get x equals 0 and y equals 0. So let's just put that. So this is how we're going to show that. When t equals 0, x and y are both 0. Let's try this one. Okay, when t is equal to 1, then x is equal to 2 and y is equal to 3. 2 and 3. Okay, sorry about that. And when x is equal to 2, sorry, when t is equal to 2, x is equal to 4 and y is equal to 6. And when t is equal to 3, x is equal to 6, and y is equal to 9, and so on. Okay, so let's try and plot some of these. So when t equals to 1, we have 2 comma 3. So that might be somewhere like that. And then when t is equal to 2, we have 4 comma 6. That might be something like that. And then when t equals 3, we have 6 comma 9. And we have something like that. And then we could continue t equals 4, t equals 5, t equals 6, and so on. And we could even do t equals 1.5, which would be between 1 and 2, and that would, we put in t equals 1.5 here and t equals 1.5 here, and we'd get a value for x and y. So here, we can say that we also have a curve. It would be a continuous curve, probably a straight line. Probably looks like this. And but this is not the standard way that we know to generate a straight line, but it does work. So we can just put in different values of t and get out different values of x and y and plot those, and we get a straight line. Now there's something a little bit different about this, and that is since t usually we consider it to be increasing from 0 to whatever we're going to increase it to, we kind of get a direction in this line. Like normally when we talk about the equation of a line or the equation of, or a line or a curve, we don't usually think of there's a direction, but here there's kind of a direction if we consider t to be increasing, then these points move in a particular direction. They don't move this way, they move this way. But anyway, when we put in a particular t, we do generate both an x and a y, and so we do get a point. So we can say that this is also the equation for, or a pair, maybe we could call it a pair of equations for a line. So this is probably a line, and we can say that this pair of equations generates this line in much the way that we say that y equals mxb gives us a line. So since this is not the standard way to write the equation of a line, we call it the parametric equation of a line, or the parametric equations, actually, I should say, of a line, and t is called the parameter. Okay, so let's take a look at this in the book. It's called Parametric Equations of Lines. And, well, we just had x equals something and y equals something, and both sides, both on the right-hand side, they were both functions of t. What were they again? So it was x equals a function of t, it was 2t, and y was a function of t, it was 3t. So in the book, they just call this function f of t, and this function g of t, right? We can call it anything we want, f, g, whatever. So, but anyway, the point is we have x as a function of t and y as a function of t. We can call those functions anything. We can call them f. And g, we can call them whatever we want. So in general, we're not going to stick with just 2t and 3t. We're going to allow that x is some function of t and y is some other function of t. So actually in this first example, it's a little bit confusing, I think, to do this with the first example, but that's what they're doing. So let's just go through it. My example was much simpler, but here they're saying, suppose x is this function of t and y is this function of t. Well, who knows what these look like, right? We don't really know what they look like. But they are, nonetheless, this is a function of t, obviously, it has a t in it. And this is a function of t, it obviously has a t in it. So whatever they are certainly, whatever, we don't know what they look like maybe, but they are certainly functions of t. And so, as t changes, x will change, and as t changes, y will change. And we can do the same kind of thing that we did here. We can check when t is 1, what is x and what is y? When t is 2, what is x and y? When t is 3, what is x? We can put in whatever, any value of t we want, and figure out what x and y will be. And so we can do the same thing here. Put in any value of t and figure out what corresponding x is, and put the same value of t in here. What's the corresponding y? And then we can plot that point, x comma y, that we get. And then we can change the value of t, put a different value of t in here, and a different, put in a value of t in here and the same value of t in here, and get another x, y, and plot that. And we're going to get some kind of points. We're going to get, when t is one thing, we'll get 1 point. When t is another thing, we'll get another point. When t is another thing, we'll get another point, and so on. Here, they're just limiting the t to some range, which we can do if we want to. We could say, well, I'm only going to put in t's between something and something. Here they're using, unfortunately, 2 pi, which sounds a little confusing, but anyway, we can limit t, the values of t that we're going to put in here, if we want to. So anyway, the point is that we're going to get some points. And it turns out that if you do this, that you will actually get a circle, which is kind of interesting, but we maybe wouldn't expect it. But it does turn out that the points fall on a circle. And if you want to show that, you could just take, if it's going to be a circle, then it means that if you square this plus you square this, and you add them, you should get a constant. So, that's a little confusing, but we know that if we take x squared and y squared, and we end up getting a constant, that means that x and y lie on a circle. So we could try that here. We could take x squared, which means take this squared, and then take this squared, and add them, and if we get a constant, then that sort of implies that all the solutions to this lie on a circle. Okay, so maybe we can do that. And so here they try and do that. And I don't know, I think we can see that we can probably factor out 2 squared out of here and 2 squared out of here. So then we get the 2 squared comes out, and we get cosine t squared plus sine t squared. Maybe you don't remember this, but that equals 1. So anyway, let's not worry about this. It does turn out that these two parametric equations do generate a circle. As I said, this is an unfortunately sort of confusing first example to do, and my example was much more straightforward. We just had this function of t and this function of t instead of this function of t and this function of t. Okay, so let's not get confused by their relatively confusing equation. Okay, now we're not limited to just x and y. We could talk about 3 dimensions, and so we put in a value for t, we'd get an x, put in a value for t, we'd get a y, put in a value for t, we'd get a z, and so we get a point x, y, z, which would be a point in 3 space. So the same kind of idea of parametric equations can generate points in 3 space. So she says here, parametric equations may be used as readily to describe curves in R3, in other words, in 3 space. A curve in R3 is a set of points whose coordinates x, y, and z are given by this kind of function. Or sorry, this set of parametric equations. Okay, so just like we can have 3 dimensions here, a lot of times in data science, we want to talk about many dimensions. Of course, we can't draw it then, but still we often have many variables or many dimensions, and we can easily extend this, like the first dimension, instead of calling it x, we could call it x1, and this could, instead of calling it y, we call it x2, and this could be x3, and then we could have x4, x5, x5, x6, x7, and so on. We could go as far as we needed to, depending on what our data was. So we could go, for example, they say, to 128 variables or 4 variables or whatever. And the way that we would specify the parametric equations is the same way. We'd have x1 equals one function, x2 equals another, x3 equals another, keep going until we get to x128 equals some other function. So it's kind of simple, in a sense, to think about how we would describe a kind of curve in R128. Okay, so she says the advantages of using parametric equations are twofold. First, they offer a uniform way of describing curves in any number of dimensions, so not just 3 dimensions, but 4 or 128 dimensions. And second, they allow you to get a dynamic sense of a curve. That means, like we said before, we said that if we consider t to be time, that's usually why they use t, because they're talking about time. So time, we generally think it increases. So you might start at t equals 0, means time equals 0, then t equals 1 might mean after 1 second, and t equals 2 would mean after 2 seconds. And what we get is, as time increases, this point is moving along this line, but in this direction. So usually when we're talking about equations of lines, we don't have that sense of direction. But this sort of enables us to have a sense of the direction of the curve, which is not normal. And the same thing here in this kind of confusing example. As t increases, we can say as t at 0, the point is here, and then it moves, but it moves along this curve, but in this direction. So she says, second, they allow you to get a dynamic sense of the curve. Dynamic means kind of moving in some direction. If you consider the parameter variable t to represent time, and imagine that a particle is moving along the circle. according to the given parametric equations, according to these equations, or according to these equations. Okay. You can represent this geometrically by assigning a direction to the curve. So that's kind of an advantage to parametric equations, that they have a kind of direction, or that you can think of the fact that there's a direction. Okay, so now we know what we mean by a set of parametric equations, and that a set of parametric equations can generate a curve or a straight line. So here, in this example, it kind of seems like it might have generated a straight line, although we are uncertain of that. And in this example, here, according to their argument, this doesn't generate a straight line. According to them, it generates a circle. So it seems like sometimes parametric equations will generate straight lines, and sometimes not. Sometimes they'll generate some other curve. So our next question is, how can we generate the equation of a straight line? How can we make sure that we're generating the equation of a straight line? Okay, so here they say first convince yourself that a line in R2 or R3, but in R3, this is R3. So here we have R3, and maybe we have a line here. So they're saying a line in R2 or R3, convince ourselves that it is uniquely determined by two pieces of geometric information. A vector whose direction is parallel to that of the line. So typically, when we're talking about a line in the plane, we often say that a line is determined by 2 points, right? Once we know 2 points are on a line, we know what line that is. But here we're saying a line can also be uniquely determined by two pieces of geometric information. And what two pieces are they talking about? One is a vector whose direction is parallel to that of the line. And two, any particular point lying on the line. So what does that mean? So, okay, suppose I want to describe a unique line. So what I can do is I can say, okay, that line is parallel to some vector, let's say this vector. So the line must be parallel to this. Well, that doesn't specify what line I'm talking about, because there are many lines that are parallel to this vector. So it could be this line, but it could also be some other line. It could also be some other line. It could be, there's actually obviously an infinite number of lines that are parallel to this given vector A. So that's not enough information to determine a unique line. But if I say it's parallel to this vector and it goes through a particular point, then there's only one such line. For example, suppose I say it has to be parallel to this vector and it has to go through this point. Then there's only one choice, right? So that's what they're saying. They're saying, first convince yourself that a line in R2 or in R3 is uniquely determined by two pieces of geometric information. A vector whose direction is parallel to that of the line. So if we're given a vector and we say the line has to be parallel to that vector, and we're also given a particular point lying on the line, then we have a unique line that will satisfy those two pieces of geometric information.